Welcome back. Today I will discuss uniform continuity. But today's topic is I will discuss uniform continuity by uniform noun. What is uniform noun? And use of uniform noun in uniform continuity. Today's goal of topic is this. This type of knowledge actually very conceptual and very important for higher study. At first, I will see what is the uniform norm. Actually, uniform norm used to check the sequence of bounded function. And we all of us know what is the bounded function. A function is bounded if image of the function is bounded. We all of us know uniform norm actually used to check the sequence of bounded function. Now notice what is the uniform norm. Uniform norm is if phi is a bounded function, then we define the norm on the set uniform norm on the set capital A as norm on the set A equal to supremum of the image phi x. Supremum of the set image where x belongs to capital A, and if m greater than 0, then norm of the set on the set A less than equal to A. And this is if and only if condition. Norm of phi x on the set A less than equal to A means if and only if absolute value of phi of x less than equal to m. This is true for all x belongs to A. And a sequence of bounded function on the set A, which is actually subset of R, converges uniformly to the function f if and only if norm of fn minus f tends to 0, and this tends to 0 as n tends to infinity. This is the uniform continuity. Definition of uniform continuity in nonlinear space. Okay? That implies this means supremum of absolute value of fn x minus f of x tends to 0 when x belongs to closed interval ab. This means West test m test. In sequence of function supremum x belongs to ab, fn x minus fx, this is actually mn. Consider it in sequence of function, this term is considered as mn, and we all of us know if mn tends to 0 as n tends to infinity, then we can tell the sequence of function is uniformly convergent. That means actually in sequence of function, to define the sequence of function is uniformly convergent or not, actually use the uniform norm or sup norm. The function defined on this norm. Okay? I hope my all viewers have understood why in sequence of function to check uniform continuity, why mn test has used. Actually, this value in sequence of function, since this value is one number, so in sequence of function this value is defined as a mn, and when this mn tends to 0, then the sequence of function converges uniformly. As for example, consider f1 fnx equal to x over n. Obviously, x over n is not bounded on the set R. But if we consider the set A equal to close 0, 1, then the pointwise limit of sequence of function x over n is actually 0 function, means f equivalent to 0. Then apply norm of fnx minus fx, which is equal to supremum of, by definition of norm, this is equal to supremum of fnx minus fx. Here fx converges to 0. That means this is actually supremum of fnx. This is equal to supremum of x over n such that x lies 0 less than x less than equal to 1. Okay? And in this interval, this value of supremum is 1 over n. Therefore, norm of fnx minus fx actually goes to 0 as n tends to infinity. So, on the interval close 0, 1, the sequence of function fnx converges uniformly on the set close interval 0, 1. Now consider second example, x be a metric space and C infinity x is set of all function which is defined from x to C such that f is continuous and bounded. Then C infinity close interval 0, 1 is always equal to C 0, 1. Obviously C infinity is a vector space. Just think, because this is very easy, why C infinity is vector space. I have defined in my previous video why C infinity is a vector space. Now consider sup norm u infinity equal to supremum x in x, norm of absolute value of ux. Obviously this sup norm is a norm in C infinity x, and in this sup norm C infinity 0, 1 and C 0, 1 actually same. Consider two vector u and v in C infinity x, then the sequence un converges to u in C infinity x. That means, that imply norm of un minus u in the sup norm tends to 0 as n tends to infinity, and norm of un minus u in that sup norm tends to 0 as n tends to infinity. That means supremum of unx minus ux tends to 0 as n tends to infinity. Okay? And this is true for all x. That means here x is independent, and actually this is definition of uniform convergent, because uniform convergent means for all epsilon greater than 0 there exists capital N such that n greater than equal to capital N, absolute value of unx minus ux less than epsilon. In this norm, actually point does not matter. This imply obviously this. So in C infinity x, always convergent means always this is uniform convergent. That means this means actually un converges to u uniformly on the set x. Actually this condition is if and only if condition. In this norm, convergence means always uniform convergent on the metric space X. I hope my all viewers have understood this part clearly. Okay. Our next example, this is very conceptual and basic but very interesting. Here X be a metric space and consider A which is subset of this metric space X, and for any X in the set in the metric space X, define D of X equal to infimum distance of the set D of XY such that Y in the set capital A. Then X which goes to D of X comma A. Here A is the subset of X. Prove that this type of mapping is a uniform continuous. Here the set D of X comma A equal to infimum distance of D of X comma Y such that Y in the set A for any X comma Y belongs to the metric space X. We can write D of X comma A. We can write this is as D of X comma Y plus D of Y comma A. Now, by triangle inequality, D of X comma A which is less than equal to D of X comma small a which is less than equal to D of X comma A y plus D of Y comma A. Here A belongs to capital A. Now take the distance infimum over the set small a belongs to capital A. Then D of X comma capital A which is less than equal to D of X comma Y, and if we take infimum distance then this is plus D of Y comma capital A. Now absolute value of fx minus f of y to prove uniform continuity. Obviously this is means D of X comma capital A minus D of Y comma capital A, and by this inequality this is less than equal to D of X comma Y. Okay, and notice this mod of f of x minus f of y less than equal to mod of x minus y. This is actually, this imply f is Lipschitz function, and we all of us know Lipschitz function always be uniform continuous function. So this type of function is a uniform continuous function, and uniform continuity always imply continuity. So x map to D of xa, where D of xa equal to infimum distance of the set D of xy such that y belongs to capital A. Obviously this type of mapping is a uniform continuous function. I hope my all viewers have understood this type of function, this type of mapping. Okay? Our next theorem, this theorem is very important and very conceptual. The statement of the theorem is, let xj and y rho be a metric space and y rho be a complete metric space, and the set A is dense subset of the set X, and consider one mapping f from A to y which is continuous function. Then f can be extended to the metric space X as a uniform continuous function. Actually, we have to prove f can be extended to a uniform continuous function. For this, consider one mapping G from X to Y, and we have to prove actually this G is uniform continuous. uniformly continuous, where given the mapping f which is defined from a to y is continuous function, and where this a is actually dense subset of the a, but we have to prove this f can be extended to new function g which map from x to y. We have to prove g is uniform continuous. This, consider gx equal to fx for x belongs to a, but when x not belongs to a, then what I will take? This is interesting. Given the subset A is a dense subset of the metric space X, therefore obviously there exists a sequence of element xn in A such that the sequence xn converges to X, and we know every convergent sequence is a Cauchy sequence. Then, and since f is uniformly continuous function, then xn Cauchy sequence means obviously for uniformly continuity, the sequence fxn is also Cauchy sequence. Since f is a uniform continuous function, so we all of us know Cauchy sequence always map to Cauchy sequence. Since given the metric space Y is a complete metric space, therefore obviously this Cauchy sequence is convergent to a limit. So f of xn is a convergent to a limit point y which belongs to the set capital Y, and consider this limit, the limit of f of xn equal to g of x which is actually equal to y. Now I will say this g is well defined. For this, consider another sequence in the metric space X which converges to same limit means X. Then we have to show actually limit fxn equal to limit fxn dash equal to gx. We all of us know limit fxn means this is equal to gx, but now we have to show limit fxn dash equal to gx. For this, since xn dash converges to x, that means obviously d of xn dash tends to 0 as n tends to infinity. That means obviously d of xn comma xn dash less than delta for n greater than equal to capital N, and that imply obviously a rho of f of xn comma f of xn dash tends to 0 as n tends to infinity, and this imply obviously limit fxn equal to limit fxn dash. That means if we consider another sequence which converges to same limit, then limit of fxn equal to limit of fxn dash which is equal to gx. That means obviously g is well defined. Now we have to prove this g is uniformly continuous on the whole metric space X. But since the function f is uniformly continuous on the set A, capital A, then given epsilon greater than 0, choose delta greater than 0 such that for all x comma y belongs to capital A. Since f is uniformly continuous on the set A, that means distance between x and y less than delta, that imply rho of f of x comma f of y less than epsilon, and this is true for all xy belongs to A. We have to show the function g is uniformly continuous on the set X. For this, consider two arbitrary points A and B in the set X, capital X. Then obviously there exists a sequence an bn in the set A such that limit an equal to A and limit bn equal to B. That imply limit f of an equal to f of A and limit f of bn equal to f of B. Okay? And since limit of an equal to A and limit of bn equal to B, that means distance between an comma an bn less than delta. Okay? That imply distance between f of an comma f of an dashed, here bn not an dashed, here bn less than epsilon. Okay, and this is true for all n greater than equal to capital N. Since we have to prove G is uniform continuous on the set X, actually we have to prove this inequality. For this, f of an equal to y, which is actually equal to g of x, and f of bn equal to y dash, which is also equal to gx. Then consider epsilon greater than 0 and distance between y and y dash less than delta, and consider this delta distance is actually equal to epsilon. Then rho of y comma y dash we can write by triangle inequality. This is less than equal to rho of y comma f of an plus rho of f of an comma f of bn plus rho of f of bn comma y dashed. Okay, and by this inequality we can tell this part tends to 0 and this part tends to 0. And I have considered rho of y comma y dash less than delta, which is equal to epsilon. Therefore, this is less than epsilon. Therefore, our proof has done. The function g is uniformly continuous on the set X. I hope my all viewers have understood this type of proof. This type of extension theorem actually very important. I hope my all viewers have understood how we have to define this type of mapping. This defined part is very important. Okay? Well, this type of concept actually very important for higher study. So I will highly recommend you, please see and understand this part clearly. Okay? Well, today I will stop here. In my next video I will discuss this type of concept briefly. Actually this type of concept very important for higher study. Okay? See you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.